So today we're going to talk about plate boundaries, and it's a huge topic, so I'm going to assume a base level of knowledge of understanding what lithospheric plates are. So it's made of the solid crust plus the solid upper mantle. So when we talk about oceanic crust or continental crust, we're often talking about that whole plate, which also involves the top part of the mantle, and we just refer to it as a tectonic plate or that piece of lithosphere. It is important to know that we have oceanic plates and continental plates, so I'm going to assume that base knowledge, but let's talk about what happens at those different boundaries. I'm also going to show you what to look for on like a satellite map so that you can identify some of these features like on something like Google Earth or Google Maps. All right, so we're going to start with a divergent plate boundary. So I have limited space, so I'm going to not be able to write down everything, but this would be a divergent plate boundary. So this is when two plates are moving apart from one another. And this is kind of a unique one because it really is a progression. So anytime you look at a divergent boundary, it's somewhere in that progression. And it will eventually continue on and develop out to a full ocean, starting from just what we call a rift, which is just where a piece of continent is being stretched. So let's show what that progression looks like. And then I'll flip to Google Maps and show you some examples of where that exists on Earth and what that looks like on that image. All right, so what we do is we actually start with a piece of continental lithosphere, right? So nice and thick. And we're going to put some tensional stress on that. That's the first thing that happens. And so when that happens, we start to stretch our crust. And so the second look to that is going to do something like this, where it just starts to thin. Okay, so we've started to stretch that. And we know that underneath our lithosphere, we've got some mantle that isn't quite so solid. And so this mantle material is going to make its way up, and you might start to get some little volcanism in here, really tiny stuff. This is called rifting, right? We're starting to rift this area apart. Now, eventually that might stretch further, and it might start to drop below sea level or become a low spot where water is collected. And so the next phase in this might look something like this. I'm going to do in the upper right hand corner because I want to use the bottom part and have more room for that. So let's say that our crust eventually does something like this, or it's even thinner. And now we are really starting to break this apart into possibly two different plates. We might fill in this with maybe some ocean water. So I'm going to show you an example of that. And we still have, of course, our material coming up. And what's going to happen is as these now two plates break apart, this molten material is going to come in and cool right here and form new crust. So we're just starting to form maybe some oceanic crust here. It's going to break apart and then more crust will form. And so when you continue to do that, what eventually happens is you end up with something, and I'm over exaggerating some of these features, that looks like this. Okay, so now I've got a very wide ocean. So here's my ocean, and I've got continental crust on either side. So this continental crust is what started way back here a long time ago. I still have my arrows moving apart. So these now two very distinct plates, which are made of continental crust and oceanic crust out here in the middle, are still moving apart. And I'm still getting this molten material coming up in here. It's going to cool as it hits that cold ocean water, form new crust, continue to split. More comes up, right? So the crust way out here is what originally formed right in here. It's just been spread apart there. You'll notice that a couple things. I have drawn the center point kind of sticking up like that. Your lecture class will get more into this, but basically this material is really hot. And as it cools, it starts to sink down. And so because it's really warm and kind of lifted up there, it ends up forming what we call a mid-ocean ridge. This is our mid-ocean ridge. And if we think about this in 3 dimensions going in and out of the board, this would be like two plates like this or two plates like this would be lifted up. So you would form kind of a mountain range, right? So this whole area would be lifted up and you have this long mountain range. And I'm going to show you an example of what that looks like on Google Maps in just 1 second. Okay, so that's a quick progression from what we just have this like crustal thinning that's just starting to stretch apart. So I'm going to call this kind of step 1 here, and I'm going to reference this in a second. And then we have continental rifting, where we start to get some volcanism in there. And then this is I'm going to put a 3 next to that for your reference, where we formed this very narrow C, because you'll see that this is happening in and out of the board. So it isn't just a circular feature, but it would extend in and out of the board and form like this very narrow body of water. And then finally, as that continues to open up, you'd form a full-fledged ocean. And so we're creating our ocean crust here, and I'm going to call that 4. All right, so now let's flip over to Google Maps and take a look at what this looks like. All right, so now we're to Google Maps, and in our divergent plate boundary, if you looked at phase 2, this is when we just had that continental rifting. Here's a really good example of what to look for. We actually have this divergent boundary. I'll talk more about one of these in a little bit, coming up through here in the ocean, and it extends into here. And really the big clue is that you've got these lakes forming. And so these are going to be this low spot. This whole area is being rifted apart. And there are some volcanoes in here that you would get some information about. And then just the fact that we have these low spots with all this water collecting is a really good indication that the elevation is low and these two pieces of crust are being like kind of pulled apart there. So that's what rifting would look like on Google Maps. If we switch over to the next location, here, this is that kind of phase 3 in our board work that we did. And you'll see you have this very narrow C here with consonant on either side. And you can actually see in the very center, this is where that boundary would be between one plate over here and one plate over here. So again, that's what that long, elongated, narrow C might look like. Our next phase, so phase 4, is when you have a big ocean. And what you're looking for there is you'll see this like linear feature that stretches. And I can actually trace that. If I continue to go up, you'll see that that linear feature continues. It's a little easier to see when you zoom out, actually, but you'll see that I can continue up. It kind of jumps over here, but it really is separating consonant, bunch of ocean, the plate boundary, bunch of ocean, and consonants there. So a really good indicator. We can just keep following that right up the center of that ocean. So that's what ocean to ocean divergence looks like. Okay, so now we're back to our board and we're going to talk about convergent plate boundaries. All right, and this of course is when two plates come together. And this one gets a little complicated because instead of the progression that we just talked about, this is going to be dependent upon what type of crust is involved. So different things will happen. So let's say that we have two pieces of continental crust. So I'm just going to do C to C because of my lack of board space. And let's say that we've got these two pieces of continent that are headed toward one another. So this would be like two similarly sized vehicles, like two big trucks. Let's say that they have a little head-on collision at like 10 miles an hour, everybody's fine, but we're gonna get some of the hoods are gonna kind of buckle up on one another, if you can picture that. And so ultimately, what you're going to get is something that looks like this. Okay, so it's gonna rise up and create a really high elevation mountain. And this is all mechanical, right? It's just smashed into one another. When I do this, I also draw a root down because it needs that root to support the weight of the overlying material. And again, you get into more detail in class on that. If I look at something like this, there is no volcanic activity. So in the last example, you saw some volcanism coming up there in the center, but there's really no way for that to seep its way through. We just have a lot of compression and this mountain building. So you build a mountain, but there's no volcanism involved. All right, so that's what convergent continent to continent looks like. If I go over to ocean to continent, This is a little different because now I don't have two similarly sized vehicles. I have one, the oceanic crust, that's going to be more dense and thinner. And so when these approach one another, what will happen? So here's my thicker continental crust and here's my thinner oceanic crust. So we'll just draw a little ocean in there. What will happen is the oceanic crust will actually subduct. So this is called subduction, super important word. You'll hear it a ton in your geology classes. Okay, so it dives down underneath that less dense, kind of more buoyant continental crust. All right, so it's a little more complicated than this, but what we're going to say is that this plate is going to generate a melt. How that does that, you can learn about in your lecture class, but we're going to produce a melt there. And so this melt here is going to rise up because, of course, it's really hot, right? So it's going to rise up and it's actually going to form a magma body underneath here, which could cool and form something like a granite, right? So it's going to be underground magma body. But also, before that cools, it's going to feed a volcano at the surface. So this is interesting because now we still have our convergence. Our two plates are coming together. One is subducting. We're creating a mountain still, mountain over here, but this one is volcanic. So it's a very different looking situation. And we also have to think about this again in 3 dimensions. So if we think about this subducted crust as a slab or a piece of paper that we're shoving down underneath this continent, and think about that piece of paper and that melt generating all along that leading edge. So this slab again is in 3 dimensions. And so we're going to melt that at the end, and then it's going to rise up and create a series of volcanoes, right, going in and out of the board. And so you'll see this chain of volcanoes that are generated right along the coastline. So that's ocean to continent. And then finally, we're going to look at ocean to ocean, which is actually very similar, to this one up here. You're still going to get subduction. It's just going to be subducting under oceanic crust. So one of the plates will subduct, something like this. And now, so let's do our arrows, sorry. There we go. Now, when you generate this melt, here it's going to rise up and it's going to go through this thin oceanic crust and it's going to create a little volcano on the bottom of the ocean floor. Right, so it's going to keep growing, and now instead of having a volcanic mountain on the continent, you have a volcanic mountain on the bottom of the ocean that, if it pops up, is going to turn into an island. So it's a volcanic island, and it will also be a chain, just like the chain of volcanoes on land. So that oceanic crust dives down, and it melts all along that edge, and you produce a chain in and out of that. And you can always tell which one is subducting because it's going to be the one that doesn't have the volcanoes on it, right? So this one has the volcanoes on it. The other one is the one that's subducting. Now there's one feature here that's quite important that I didn't mention. It's going to really help us identify this. And that's going to be what's called a trench. And you see it in both spots here. So here's a trench, I'm going to mark that with a T. Here's a trench, mark it with a T. And so what happens is right where this oceanic crust subducts, you're going to get a really deep part of the ocean. So the Marianas Trench is kind of the famous one. It's the deepest spot of the ocean. And it's just because it's where these two subducted, or this subducted plate meets the plate that's not subducting. And so we can look for these trenches, and it's a really good indicator that you have subduction. Now remember, just like we create a chain of volcanic mountains or a chain of volcanic islands, this trench is going to be in like a chain, right? So it's going to be a linear, really linear, deep feature, which is why we call it a trench. So it's interesting because all 3 of these produce mountains, right? Just an elevated area. One is kind of a mechanical process, no volcanism. One's a chain of mountains on land, all volcanic. One's a chain of mountains on the bottom of the ocean, creating volcanic islands. And so now let's skip over to Google Maps and I'll show you what some of these features look like there. So now we can take a look at what continent to continent convergent looks like. And what you just really need is a big hunk of continent with a plate boundary. So you'd be able to look on a tectonic map that would show you the plate boundaries. And if the location that you're looking at has a really big mountain range that kind of mirrors that plate boundary, it's a really good indicator that you have continent to continent convergence there. And then the next one that we looked at, we talked about trenches. So I have two examples of a trench. So here, this is what a trench looks like. There's one example. And then our secondary example looks something like this. And so the difference you can see is that in this example, we've got ocean on both sides. In the first example, we have ocean over here and a continent over here. So here's a really good indicator that we've got oceanic crust, a trench, and then some continent. So we likely have ocean to continent convergence that's creating that trench. Over here, we likely have ocean to ocean convergence. That's what's creating this trench here. And also these little islands are a good indicator. They're probably volcanic and they're being generated by that melting that we talked about. I wanted to skip back to this idea of ocean to continent convergence. One of the other things we talked about was that there might be there would be a chain of volcanoes here. So there is a mountain range here. That's why it's this kind of brownish color, as opposed to the flatter kind of greenish plains out here. But one other example, something you can look for, here's in a different area. So we've got our ocean out here, and you'll notice these white peaks. So those are snow-capped. The reason they're snow-capped is because they are higher elevation, and that's because they're little mountains that are volcanic. And you'll see that they kind of run linearly here, parallel to the ocean. And that's because out here, we likely have subduction that's creating a chain of volcanic mountains. So that's another thing that you can look for. And now we can cover our third plate boundary type, which is a transform plate boundary. So I'm going to write transform here. And this is when you have two plates that slide past one another. So there's really no good way to draw this in a cross section because they become in and out of the board. And from the top down, it's going to be a little funny to look at. So I usually like to represent this with two blocks sliding past one another. So here is this block here, and then here is another block there. And if I finish off that block, something like this, you can see that I now have two land masses that are just sliding by one another. So, still use this color. So this block is going this way, this block is going that way, and it's just this sliding motion. So this is a place where you do generate things like earthquakes. We haven't really talked about that, but you do produce earthquakes at all of these types. You won't produce volcanism here. And the reason why is because the sliding action, there's really no way for this material to get up in there. It's just sliding right by. There's no gap created, or you're not melting anything like with convergence. And so there's no volcanism and really no mountains either, because it's just this pure slippage. But what I will tell you is that oftentimes these faults aren't straight. And so what will happen is, instead of kind of this like clean sliding motion, if you were to bend your hand in one direction, and if you slide it open one way, you'll create like an opening. If you push the other way, you actually get compression. You'll feel that in your hand. So just take your hands and kind of bend them, and then try to experiment moving, let's say, your right hand forward and then move your right hand back. And in one case, you'll open up a hole, and in one case, you'll actually create compression. So if these get wiggly on us, sometimes we open up like small basins, or if we have a bend, we can actually compress the land there and pop up little mountains. So just be aware of that. But a true transform plate boundary that's straight will really just produce this slippage action and no volcanism and no mountains. Now let's go look at Google Maps for a few examples. And then our final one to talk about. And so now let's talk about trying to find a transform plate boundary. So this can be a little more challenging. There really aren't some of these features like trenches or volcanic mountains to look for, but often we look for offset features because remember, these are a sliding motion is occurring. So here I actually have this stream that's coming down, and you'll see it meets our linear feature here, which is a plate boundary. And then you'll see that as it approaches that, it is offset there. So it actually follows the fault or the plate boundary there and then is offset. And that's because this plate has moved kind of down and to the right, and this plate over here has moved up and to the left. And so it's offset that along that transform boundary. So looking for offset features really is a great way to locate these transform boundaries.